Welcome to the story of Enrico Fermi, a man uniquely hailed as the last double-threat physicist. In an era of increasing specialization, Fermi stood alone, mastering both the complex abstract world of theoretical physics and the hands-on precision of experimental science. This presentation explores the life, groundbreaking science, and enduring legacy of the architect of the nuclear age. From the chalk-dusted boards of theory to the physical realization of atomic power, we examine how one individual reshaped our understanding of the universe. Join us as we uncover the brilliant mind that bridged the gap between thought and reality, leaving an indelible mark on history. This executive summary charts the four pivotal phases of Enrico Fermi's extraordinary life. We begin with the prodigy, 1901 to 1925, where a young Fermi mastered mathematics to a doctoral level while overcoming deep personal grief. Transitioning to the Roman School, 1926 to 1938, he established Italy's premier physics institute and unlocked the secrets of beta decay and slow neutrons. By Phase 3, the atomic age, 1939 to 1945. Fermi fled to the United States to engineer the world's first nuclear reactor and serve as the Manhattan Project's ultimate problem solver. Finally, the legacy, 1946 to 1954, celebrates a beloved teacher whose name is permanently etched into the periodic table and the fundamental particles of our universe. Enrico Fermi's genius was forged in the crucible of personal loss. Following the sudden death of his brother, Giulio, in 1915, Fermi channeled his grief into an obsessive study of physics. He became a self-taught prodigy, mastering complex concepts from a 15th-century Latin text found at a local market. His focus was absolute. His wife, Laura, recalled him studying in the freezing cold, turning pages with his tongue to keep his hands warm. This discipline culminated in his 1918 academic debut. His entrance essay for the Scuola Normale Superiore was so advanced that stunned examiners declared it equivalent to a doctoral dissertation. At just 17, the boy from Rome had already begun his ascent as a giant of science. Enrico Fermi was a rare, double threat, reaching the absolute pinnacle of both theoretical and experimental physics. As a master theorist, he defined the statistical laws governing particles and introduced the weak nuclear force through his theory of beta decay. Simultaneously, he excelled as a master experimentalist. He discovered how slow neutrons dramatically increase nuclear capture and famously engineered Chicago Pile 1, the world's first self-sustaining nuclear reactor. While most physicists dedicate their lives to mastering either abstract mathematics or tangible engineering, Fermi dominated both domains. From defining atomic properties to inducing artificial radioactivity, his genius bridged the gap between pure mathematical thought and monumental experimental results. In 1926, Enrico Fermi and Paul Dirac defined the statistical laws governing particle behavior by applying the Pauli exclusion principle to an ideal gas. This breakthrough distinguished between two fundamental classes, fermions and bosons. Fermions, such as electrons and protons, possess half-integer spin and cannot occupy the same quantum state, forming the rigid structure of matter. Conversely, bosons like photons have integer spin and can congregate in the same state. This model solved classical physics mysteries, explaining the heat capacity of metals and the structural stability of collapsed white dwarf stars. By identifying these rules of matter, Fermi provided the framework for understanding the very fabric of our universe. To restore Italy's scientific prestige, Senator Orso Mario Corbino, nicknamed God Almighty, assembled a world-class team at Rome's Royal Physics Institute. At the center of this cast of characters stood Enrico Fermi, known as the Pope because his scientific pronouncements were considered infallible. Fermi's Via Panisperna boys featured a colorful hierarchy. Cardinal Vicario Franco Rossetti led experiments, while the brilliant Ettore Majoraner served as the Grand Inquisitor of theory. Rounding out the group were researchers like Basilisk, Emilio Segre, Cucciolo, Bruno Pontecorvo, and electronics expert Edoardo Amaldi. This collective combined theoretical depth with experimental rigor to conquer the new frontier of nuclear physics. In 1933, Enrico Fermi resolved a burgeoning crisis in physics, the apparent violation of energy conservation during radioactive beta decay. While the missing energy from emitted electrons baffled his contemporaries, Fermi hypothesized it was carried away by a nearly invisible particle he dubbed the neutrino, their little neutral one. He proved this particle was created at the precise moment of decay, a breakthrough that introduced an entirely new fundamental interaction, the weak nuclear force. Despite its brilliance, the journal Nature famously rejected his paper for being too remote from reality. Today, this masterpiece is recognized as the paradigm shift that defined the very structure of subatomic interactions. In 1934, Enrico Fermi transitioned to experimental physics and encountered a baffling anomaly. His experiments were inexplicably more successful on wooden tables than on marble. This observation led to the Fermi insight. While fast-moving neutrons often bypassed their targets, Fermi discovered that hydrogen-rich materials, like paraffin or water, acted as a mechanical brake. These slowed down neutrons, which he described as a solution of slow neutrons, were captured by nuclei 100 times more effectively, resulting in a massive surge in induced radioactivity. This breakthrough earned Fermi the 1938 Nobel Prize and remains the fundamental blueprint for modern nuclear reactors, demonstrating that the key to unlocking atomic power lies in the precise control of its smallest particles. The rise of Mussolini's fascist regime and the 1938 Italian racial laws created an untenable situation for Enrico Fermi. While not Jewish himself, his wife, Laura, was, making their continued residence in Italy impossible. In December 1938, the family departed Rome under the pretext of attending the Nobel Prize ceremony in Stockholm. After receiving physics' highest honor, they traveled through England to board the RMS Franconia for an Atlantic crossing. Arriving in New York on January 2, 1939, Fermi immediately began a professorship at Columbia University. This flight to the New World underscores a massive historical irony. Fascist persecution actively drove Europe's most brilliant minds into American hands, forever altering the scientific landscape just as World War II loomed on the horizon. The year was 1939. News leaked from Germany: the uranium nucleus could be split. For Enrico Fermi, the dots suddenly connected. He had achieved fission years earlier in Rome without even knowing it. He began to conceptualize a monumental new reality, the chain reaction. It starts with a single slow neutron splitting a uranium atom, releasing energy and secondary neutrons. When moderated, these neutrons strike more atoms, triggering a self-sustaining, exponential cascade. This theoretical sequence transformed a laboratory discovery into a formidable force of nature, providing the blueprint for the atomic pile and, ultimately, the birth of the nuclear bomb. Hidden beneath the University of Chicago's football stands, Enrico Fermi's team secretly constructed Chicago Pile, one in an abandoned squash court. Built by hand over 2 weeks using 57 distinct layers, the pile's anatomy was a feat of precision engineering. It featured 360 tons of graphite blocks as a moderator to slow neutrons, which then struck a fuel lattice of over 92,000 pounds of uranium oxide and metal. To control the process, cadmium-coated wooden brakes served as control rods. Pulling these rods out initiated the chain reaction, while pushing them in safely stopped it. This unlikely setting hosted the birth of the first self-sustaining nuclear reaction. December 2, 1942, marks the day the world changed forever. Beneath the University of Chicago football stadium, Enrico Fermi meticulously directed the withdrawal of cadmium rods, monitoring the rhythmic acceleration of radioactivity. True to his disciplined nature, he paused the high-stakes experiment for a calm lunch break. By 3:20 p.m., the Geiger counter's frantic roar signaled a self-sustaining chain reaction. After generating 1/2 watts of power, the giant was safely silenced, and the triumph was toasted with Chianti from paper cups. Arthur Compton's famous telegram confirmed the news: the Italian navigator had indeed arrived in a new world of atomic possibility. Enrico Fermi's reputation as the Manhattan Project's ultimate problem solver was cemented through 2 legendary interventions. At the Hanford B reactor, he diagnosed a mysterious shutdown as neutron poisoning caused by xenon-135. Because Fermi had wisely over-engineered the design with extra fuel tubes, the crisis was averted by simply increasing the uranium load to overpower the poison. Later, at their historic Trinity test, he bypassed complex instrumentation to calculate the atomic blast's yield. By observing how the shockwave displaced falling scraps of paper, Fermi estimated a 10 kiloton explosion on the spot, a remarkably accurate order of magnitude calculation compared to the actual 21 kilotons. Whether tackling chemical anomalies or physical forces, Fermi's practical brilliance turned potential failures into scientific triumphs. Enrico Fermi possessed a legendary ability to navigate the unknown using logic and intuition. His namesake method highlights two profound concepts. First, Fermi questions demonstrate how breaking complex problems into justified order-of-magnitude estimates can yield highly accurate results from limited data. He proved that a sharp mind could solve nearly anything by simplifying the scale, turning raw guesswork into a reliable science. Then, in 1950, he posed the Fermi paradox. While contemplating the vast, ancient universe, he simply asked, "But where is everybody?" This observation, that our galaxy should be teeming with life despite their haunting silence, remains the defining mystery of astrobiology today. Enrico Fermi's life ended in 1954 at just 53, but the Fermi effect remains a profound fingerprint on the universe. His name is etched into the very fabric of matter through fermions, half the universe's fundamental particles, and element 100, fermium. From the cutting-edge research at Fermilab to NASA's Gamma-ray Space Telescope, his influence spans from the subatomic to the cosmic. Having defined the weak force and established a standard for scientific excellence, Fermi's enduring legacy is best captured by his own belief that ignorance is never better than knowledge. Today, his name is spoken daily in laboratories and classrooms worldwide, honoring a master who bridged the gap between theoretical wonder and experimental reality.